also accept. And that means that the language that G recognizes is that G dashed will also recognize, right? So the two are equivalent in that sense. Now we can go the other way, so hence the conversely, in the opposite direction. If you so assume that G dashed accepts will recognize a certain language, then G should also recognize the same language, hence equivalent going in the other direction, proving it in the other direction. Now why should that be? All right, so we're going now we're going from G dashed. Okay, so let that be. That's what G dash looks like, you know, with the Q ripped out, missing. This one, this, yeah. Now, what is between here? Well, the label on the transition arrow is R1, R2 star R3 union R4. Okay. Well, if we then have G, well, we've got our Q rip back, right? We're going the other way. Well, that means we have to get from here to here to here. Well, there is a transition from QI to Q rip, right? And it's what is it? It's R1. But we've got that R1. We've got the R1 because here we had R1, R2 star, R3. So we've got the R1 to go from here to here. And we've got an R3 to go from here to here. Okay? So that means that we can go. So if it works, if it reaches the accept state for G dashed, it should also reach for G. Okay? So G and G dashed are equivalent. So in other words, now G dash just means that's the machine, that's the G NFA with K-1 states. And G is the machine, the G NFA with K states. Right? So if it works for the lower one, the lesser, you know, lesser number of states, it works for one more, the machine with one more state. And now by induction we proved that it worked for 2 states. So if it works for 2, it works for 3. If it works for 3, it works for 4, and so on. So we've got it. We've proved the induction proof. You know, that the induction has been shown. All right. So that completes the only if part. We use the device, the trick of using G NFAs. So this has been a rather long proof. So we have now completed the only if part. We proved the if part on the previous board. So we've now done both the if and the only if part. So we've completed theorem, what was it? 1.54. Okay. So now the claim, that was the induction. So we proved that by induction. So we finished that. Okay. And finishing the proving that the machine functioned as desired. So that was this. That was the claiming that the machine actually produced a regular expression that was correct. Okay, so we proved that, and hence the machine was correct, and hence the only if part was, you know, if that's correct, that finished off this proof. Lemma 160, that was the only if part. Okay, and once we had that part, and we've already proved previously the if part, so now we have the if and only if part proved, and therefore this theorem is complete. Now, I hope this doesn't happen too often, but I felt somewhat antsy about the lack of clarity of Sipser on some points, and this proof I was not terribly impressed by. Now, maybe part of the blame lies with me, maybe part with him. It's hard to say. So leave it to you to judge. So if you found this discussion not clear, then I assume you've got the text. So have a look at the text. You can read through this. It's almost verbatim, because it's not easy. So I've written it out with very little paraphrasing, so that you can read it yourselves more or less directly from the author. The other alternative is read the text itself, maybe a combination of both, and hopefully you can follow it. This is one of the most difficult proofs so far. So I find his wording not very clear at times, which is annoying, frustrating. Okay, right. So now we move on to an example of what we've been talking about. In other words, how to construct starting from a DFA, how do you find its equivalent regular expression? Okay. Now we're going to start. So here's a DFA that we start with. It's very simple. It's just a two-state machine. Okay. So here's the state diagram, state transition diagram, and it's a DFA, like for each state there, and for each possible symbol in the alphabet. And in this case, the alphabet's just binary, just two symbols, little a, little b, okay, and states 1 and 2. So the number of transition arrows total will be 2 times 2, which is 4. So 1, 2, 3, 4. So there are actually 2 arrows. One's for A, the other's for B. This is sort of a shorthand. Okay. So that's the DFA. So let's try to construct the corresponding regular expression from it. I run out of session and board. I won't be able to finish it, but we can get a fair way. And then the next board, we will do a second example of the same kind of thing, starting with a DFA. The second example is slightly more complicated than this one. It's very simple. Starting with a little more complicated DFA and finding its corresponding or equivalent regular expression, R. Okay. So remember, it's always it's a two-step process. You start with a DFA, you find, and it's easily done, you build an NFDA from that DFA, and then from that, using this ripping out technique, using the function convert G, you then create the equivalent regular expression. Okay, the two-step process. All right. So the first step, let's create an NDFA from this DFA. Sorry, a GNFA from this DFA.